This is a course review for History and Philosophy of Science. Please don't assume that it reviews everything we talked about during the semester. It only reviews those things that I consider to be high points, most important points in the course. The final exam will cover everything in this course review, plus, of course, the reading from both of the books during the semester. The title of the course well summarizes the scope of the course. We studied the history and the philosophy of science. We studied the history of science largely by looking at the lives of the great scientists who did the work of science down through the ages. We started really with Aristotle, but that was only to set the stage for our real study, which began with the Renaissance around 1300, 1500 AD. The date is a little bit flexible depending on just what markers one chooses as the beginning of the Renaissance. Aristotle's science pretty well held sway for about 2,000 years. But then, with the Renaissance in Europe, scientific discoveries began taking place rapidly, one building upon another, until in the space of a couple of centuries, science had radically changed. We looked at the lives of those scientists who were responsible for those changes and recognized that in many ways they were products of their times, that they were influenced by cultural and economic and social and political and gender issues. We recognized that they were very human, that sometimes the results of their discoveries depended a great deal on issues like their personality and their ability to communicate and to network, as well as their social status. We looked at the flow of history and how the history of science intertwined with the history of technology and technological developments, and how those in turn changed the societies in which those technological developments took place. The second great piece of the course was the philosophy piece, and there we looked into the question of what is science? How do you distinguish science from non-science? And what is the boundary between science and non-science? We recognize that there are a number of things that look scientific, but really aren't. Things that masquerade as pseudoscience. So how does one tell what is scientific and what isn't scientific? Is everything science? Is the study of everything science? Or is it only the study of some things? Is every method scientific, or is it only some methods that are scientific? So, between these two big pieces, history and philosophy, we attempted to understand this thing called science in the hope that it would make us better scientists, better users of science, better thinkers, better citizens in our society. One of the two textbooks that we used for the course, DeWitt's Worldviews, talked about the development of worldviews and the interactions, the clashes, if you will, of worldviews, and how worldviews came to dominate one over the other. We looked at it from that perspective, but also a little bit differently, in the sense in which we looked at the hunter-gatherer society and realized that in that society there really wasn't a whole lot of science being done, but there was close living to the natural world and therefore great opportunities for observing the natural world, much of which had to do with observing weather patterns, observing the skies in the day and the night, observing climate and how it changed over the years. The study of the heavens and the way in which they impacted life on Earth was of great interest to the hunter-gatherer society. When the hunter-gatherer society was replaced by agricultural societies, then science became an opportunity that people could explore frontiers that they hadn't had the time to explore before, because now they were settled in one place. They weren't traveling all the time. And because they had agriculture, they were able to devote some time to scientific pursuits. Agricultural societies meant that they could stay in one place. They could make observations from that one place. They could build scientific equipment. They could build technology. And they did, in fact, do those very things in the great agricultural centers on Earth. The agricultural society eventually gave way to the industrial society, the age of machines. This was, of course, the great age of technology. It was scientific advance that enabled the development of technological advance, which in turn enabled the development of more scientific advance. Think, for example, about studying the physics of the expansion of gases, and then think about how that was put into use to build steam engines where the expansion of gas drove a piston that drove the machinery that powered the industrial world. From the industrial age, we moved into the digital age. When I say we, I mean Western Europe and the United States. Many nations are still not in either the industrial age or the digital age. The digital age is characterized by information processing more than anything else. And of course, it's the age of the smartphone and the computer. It's the age in which digital information about the world can be analyzed and transmitted and printed and disseminated in many different forms. And we're not really sure where this is going to go, of course. It has enabled all kinds of technological revolutions, from the iPhones in our pockets to the ability to go to the moon and back. But it also has robbed us of many of the things that have traditionally been associated with what it means to be human. A place, a home, family, society, a tribe. So, like most things, the development of science has been a mixed blessing, a two-edged sword. Along with the development of science goes worldviews that have changed as science has developed, and science has been changed by those worldviews. They go hand in hand. And we looked at how all of that interacted and how science is dependent upon society and culture and history and leisure time and population. How such things as the Black Death, for example, impacted science, and how the Protestant Reformation impacted not only religion, but also science and technology. How leisure, how capital and capitalism impacted science. And we tried to recognize that all these things are very closely intertwined. A great deal of the course was taken up with comparing three different worldviews, what we might call the Aristotelian, the Newtonian, and the Einsteinian. We kind of use Einstein here as a figure for several figures in more modern times, meaning roughly the 20th and 21st centuries, that delved into not just relativity theory, but also quantum theory and other state-of-the-art, not yet settled theories about how things are. But let's go back and remember Aristotle. Aristotle might be regarded as the very first natural philosopher to make a big reputation for himself. Remember, philosophy was the business of asking why about many things, but natural philosophy was the business of looking at the natural world and asking why. And Aristotle was a great natural philosopher. Natural philosophers, by the way, eventually came to be called scientists, people who studied the natural world. Aristotle had some ideas which our textbook author DeWitt characterizes as a jigsaw puzzle, all of which fit together nicely and which interlocked in such a way that it would be very difficult to change one puzzle piece without changing all the puzzle pieces, especially the puzzle pieces that were at the center. And the central idea in Aristotle's jigsaw puzzle was the idea that the Earth was at the center of the universe, that everything moved around it in perfect spheres, perfect circles, because the gods wanted it to be that way. That everything was endowed with a certain essence, and that things behaved according to their essence. It was the essence of Earth to be heavy, and that meant that it moved towards the center of the world. It was the essence of air to be light and to move upward. Fire and water were the two other essentials, and they behaved according to their essence. The world had a great purpose. It was teleological. The universe was considered to be fairly small. The celestial sphere of the stars were considered to be out there, but not nearly as far out there as we now know them to be. Aristotle's universe produced a workable cosmology that lasted for almost 2 millennia. But eventually, of course, it began to crack. People began to say, this doesn't really work. The math doesn't really come out right. It's too hard to explain some of the observations that we see in the universe. It's hard to explain, for example, why Saturn appears to have horns, or why Jupiter has moons, or why Venus goes through phases, or why Mars seems to appear to move backwards sometimes. And while we can come up with plausible explanations using the existing model, it really would be easier to just discard the model in favor of another model altogether. And that, of course, was the movement from the Ptolemaic understanding of the solar system to the Copernican understanding of the solar system. And later, of course, Galileo, who is often considered to be the first scientist because he added something else to Aristotle's thinking about the universe. He added observation and experimentation. I'm sorry, not just observation, but also experimentation. Observation is well and good, and it leads to the collection of data and then to the formation of theories based upon that data. Aristotle was in favor of just that kind of science and believed that only deductive logic and observations constituted good science. But Galileo suggested that we could actually perform some experiments to see whether things that we would expect to happen actually do happen, and see if we can figure out why they happen the way they do. This eventually led to chinks appearing in the Aristotelian model that eventually caused it to collapse and to be replaced with another model altogether, what we sometimes refer to as the Copernican or Galilean model, in which not the Earth but the Sun is at the center of a heliocentric solar system. Gradually, observations began to get across the idea that the universe was much, much bigger than Aristotle had ever believed, that in fact it was so large that it was immeasurably large. As things began to change, people began to be more and more willing to consider other possibilities and other ways of understanding the action of things until we have the great revolution that was, in a sense, capped by Sir Isaac Newton. Newton mathematically expressed many of the laws that govern the functionings of the universe. His famous law of gravity, for example, and his famous 3 laws of motion revolutionized the doing of science and made science primarily a mathematical enterprise using mathematics that he invented for the sake of doing the calculations. Gradually, the Earth came to be understood, or the universe came to be understood, more as a huge machine that had been assembled by a master designer, God, who, having assembled this great machine, sort of left it to operate according to rules that he had created for it, much like a huge celestial watch might function. The Earth ticked away, the planets moved, the stars held their places in the universe, and man was kind of an inhabitant in this huge machine called the universe. And that understanding was the dominant understanding that grew out of the Renaissance. And for the 17th and 18th and 19th centuries, it made possible all kinds of new scientific discoveries, and also made possible the development of startling new technologies, machines and factories, and the ability to light cities with electricity and travel at astounding speeds that had never been dreamed of before, and to blow up many more people than we could ever blow up at one time before. And all those developments, with both their good sides and their bad sides, grew rapidly right up into the 20th century. In the early part of the 20th century, people were very optimistic about science. Lord Kelvin, you may remember, looking back on the developments of science over the last few hundred years, said that we've come a long way and things are pretty well settled now. We've really got all the answers to all the important questions. There remain only a few minor clouds on the horizon. And some of those minor clouds had to do with black body radiation, you may remember, and the way in which light is propagated. And those were two puzzles that nobody could quite figure out, but Lord Kelvin and other scientists were convinced that before very long they would have it figured out and life would go on. But the figuring out of those two little things led to a whole new kind of science, a science that had to do with the very, very small and the very, very fast, and also the very, very large. And the guy probably most associated with that would be Albert Einstein. His investigations of the nature of light led him to his famous mathematical formula, energy equals mass times the speed of light squared, which ushered in the nuclear age, but also led to all kinds of thinking about light and how it functioned and how the very tiny impacted the world in which we live. How can the speed of light be a constant? How can particles behave sometimes as particles and sometimes as waves? What is light? Is it a particle, a stream of particles, or is it waves? How do you explain the fact that sometimes it behaves as one and sometimes as the other? How is it that if we accept that the speed of light is a constant, we can understand space-time? How can we understand the way in which time appears to dilate and space appears to expand as we approach the speed of light? These questions puzzled people going into the 20th century, and many of them have been understood, but still there are huge questions that still remain. And quantum physics, along with quantum chemistry, quantum mathematics, have enlightened a lot, but certainly have not answered all the questions. So it's sort of like each one of these people opened the door to a whole huge warehouse filled with things to explore and question and think about. And some people think that, or at least made the mistake of thinking, that the warehouse had been pretty well explored when somebody would find a little door way back in a dark corner which would open up to a whole new warehouse. So that the idea that we get now is not that science has explained more and more and more of the universe, but that even while science has explained more and more of the universe, there still remains more and more and more to be explained. So the task of understanding the universe is understood to be far greater now than it was in the time of Aristotle. And this seems to be the nature of scientific investigation. We explored some of the basic concepts in philosophy of science. Let me just remind you of a few of them here. Epistemology is that part of the philosophy of science that deals with what knowledge is. How do we know? How do we know that we know? How do we accept some things as true? How do we justify that the things that we believe are true are really true? Empiricism. That's a whole set of philosophical approaches to building knowledge that emphasizes the importance of observable evidence from the natural world. What you can see, what you can smell, what you can hear, what you can taste, what you can touch. The evidence of your five senses. That forms the basis of empiricism. And we talked about how, on the basis of empiricism, Aristotle had every reason to believe that the earth was immovable at the center of the universe. But how empiricism clearly led him astray because that wasn't objectively true. Induction is a method of reasoning in which a generalization is argued to be true based on individual examples that seem to fit with that generalization. For example, after observing that trees and bacteria and sea anemones and fruit flies and humans all have cells, one might inductively infer that all organisms have cells. That might be true, but it might not be true, because what it really means is that all the organisms that have been looked at so far have cells. Remember the story I told you about the guys on the train traveling through Scotland who saw a black sheep standing alongside the tracks. Deduction differs from induction, and this, of course, was the method of reasoning that Aristotle favored. Deduction, a method of reasoning in which a conclusion is logically reached from premises. For example, if we know the current relative positions of the moon, the sun, and the earth, as well as exactly how these move with respect to one another, we can deduce the date and location of the next solar eclipse. That's deductive reasoning. And you're on pretty solid ground with deductive reasoning. It seldom leads you astray. If the premises are true, the conclusion must be true. In inductive reasoning, on the other hand, all you can say is, as far as we know. Parsimony, otherwise known as Occam's razor, we didn't pay too much attention to. We just referred to it as the idea that all other things being equal, a simpler explanation is to be preferred over a more complex one. In other words, why would you prefer the explanation that epicycles explain the retrograde motion of Mars when you can simply come up with a different explanation that Mars doesn't circle the Earth? Instead, both the Earth and Mars circle the Sun. William of Ockham was a scientist who came up with this idea, and it basically means that nature is lazy and that given choices, it'll always take the path of least resistance, or the easiest choice. Demarcation problem refers to the problem of reliably distinguishing science from non-science. Modern philosophers of science largely agree that there's no single simple criterion that can be used to demarcate the boundaries of science. It's a complex question. But how do you tell what is science, and how do you distinguish it from non-science? If only there were just one way to tell, but unfortunately there's not. Falsification is a view associated with philosopher Karl Popper that evidence can only be used to rule out ideas, not to support them. In other words, disconfirming evidence is a lot easier to come by than confirming evidence, in the sense in which it settles the issue better than confirming evidence does. To confirm something just means that you found one more way to prove that it's so, but if you disconfirm something, you've found a way to disprove it altogether. Popper proposed that scientific ideas can only be tested through falsification, never through a search for supporting evidence. So a good scientific theory, according to Popper, would be a theory that was easily testable and could be falsified. If you can't falsify it, it's not science. It may be religion. Paradigm shifts and scientific revolutions is another idea that we looked at, associated with philosopher Thomas Kuhn in his book, The Structure of Scientific Revolutions. He suggests that the history of science can be divided up into times of normal science, when scientists add to, elaborate on, work with a central accepted scientific theory, the work that scientists do every day, and briefer periods of revolutionary science when there are scientific breakthroughs, discoveries, aha moments. Kuhn asserted that during times of revolutionary science, anomalies refuting the accepted theory have built up to such a point that the old theory breaks down and a new one is built in its place in a so-called paradigm shift. So what happened from Aristotle to Newton was a paradigm shift. What happened from Newton to Einstein was a paradigm shift. These paradigm shifts characterize scientific revolutions, and they lead to the formation of a new worldview. A worldview might be called a paradigm. And so when revolutions take place in scientific investigation, you get a new worldview, a new paradigm. A very important part of philosophy of science is learning how to think well. So we spent some time talking about logic. We illustrated the logic of scientific investigation with a barrel of apples. And I said, suppose we had a barrel of apples, and we picked out an apple from the top, and it was rotten. If we inferred from that one rotten apple that the whole barrel of apples was rotten, we would be using inference to start with a specific case and move to a general conclusion. And that might well be an irresponsible conclusion, because one apple is not a big enough sample to decide that the whole barrel is rotten. And then from there we talked about how you might design a scientific investigation that would be in fact founded on good logic, good science. We thought, okay, maybe we need to know something about the science of apple packing in barrels. What temperature was the barrel stored at? What's the optimal temperature for storing apples in a barrel? Do the apples squash the apples on the bottom? Does a barrel of apples rot from the bottom up or from the top down? Do rotten apples infect one another? What is the causative organism that causes the apples to rot? Those kinds of questions would help us to form better guesses about whether the whole barrel is rotten or not. Also, sampling would help us to come to a better conclusion. So I might take not just an apple off the top, but I might take an apple from the middle and an apple from the bottom. If all three are rotten, then that would lead me to a different conclusion than if the only rotten one I found was the one on the top. Of course, as I sample more and more apples, the possibility that my conclusion that the barrel is rotten becomes stronger and stronger. And what's happening here is that I am inferring from the data to a conclusion. I'm inferring a conclusion based upon the data. And I'm inferring the best explanation for the data, which is this whole barrel of apples is rotten. It's old, or it wasn't stored properly, or something that accounts for the fact that this barrel of apples is rotten. If, on the other hand, my sampling indicates that apple after apple is good and only the very first apple was bad, then I would probably come to a different conclusion and have a different explanation that would explain why the one apple was bad while all the rest were good. In a sense, this is what scientists do with the universe. We can't sample everything. In fact, there's a lot of stuff in the universe that we can't sample at all. Nobody's succeeded in taking any samples of the sun, for example. It's just impossible, at least at the present time. To sample some of the farthest stars or galaxies would take lifetimes. So the chances are that we are not going to have first-hand empirical data on which to draw conclusions about the vast bulk of the universe. We're only going to be able to study the part that's closest to us that we can actually collect some data on it. The rest we're going to infer. And of course, inference is the way that we have to do most things in medicine. For example, you can't cut everybody open to see where their appendix is located. So you conclude on the basis of a couple of cadavers that you dissect that the appendix is located in the lower right quadrant of the abdomen. Of course, it isn't always there, and surgeons are not surprised to find it someplace else, but that's a good place to start because that's where it most often is. You can't study measles in every kid. You can only study measles in a few kids and then generalize to the rest of the kids. This illustrates how science tends to be reductionistic. It tends to reduce things down to manageable size so that conclusions can be drawn. And there's dangers in reductionism. One of the dangers is that what we're studying may be different. Another danger is that we may be so prejudiced in favor of what we think is true that we don't have our eyes open to the possibility that we might be wrong, that things might be different. So in our use of inference, we need to recognize the inherent limitations in inferential reasoning, inductive reasoning, that have been pointed out by a number of people. Hume, the philosopher. We talked about Hemphill's ravens, and we talked about Grew emeralds and some other things to help us understand the dangers of inductive reasoning and how it differs from deductive reasoning. Because we want to be logical. We want, above all things, to think well, to think clearly, to think accurately about the universe that we're observing and drawing conclusions about. This leads us to some conversation about scientific method, which of course does begin with observing the universe. Observe the stars, observe the planets, observe the oceans, observe the tides, observe your fingernails, observe your bowel movements, observe your abdominal pains, observe the measles rash on that kid over there, take a look at the tonsils of that kid over there. Make an observation. And as you make observations, you systematize them and form them into some kind of data. And then on the basis of that data, you begin to ask questions. And then, in an effort to answer the question that you're asking, you form a hypothesis, which is essentially a guess. Hopefully an educated guess, but it's still just a guess. Then you make a prediction based on the hypothesis that essentially says, if my guess is true, what should I see? And then you do an experiment to see if in fact you see that. Do I see what I would expect to see if my guess were true? So you do the experiment to test the prediction. Then you analyze the results. Is your hypothesis correct? Did it actually happen the way you guessed it would happen? Good. Now you can report your results to the larger scientific community because they are going to check what you did and see if they get the same result that you did. On the other hand, you may find out that what you observed when you did the experiment is not what you had hoped to observe when you did the experiment. And so that would suggest that your hypothesis was incorrect, that you guessed wrong. Well, you would also want to report those results because even negative data is data, and it's helpful. But again, you go back and you try again. You clean it up. You see if you can come up with a different hypothesis that answers the question. You test that one. And this is this process of doing science. And it's done by thousands of people over and over, and it's shared so that people can benefit from it, and they can test it, and they can see if it's repeatable, and whether they get the same result that you got. And if so, after repeating it over and over and over, the consensus emerges that your guess was a good guess. This is probably true. And then from this, people can begin to form theories about why it's true and predict about what will happen in the future based upon this theory. And it might even lead to the formation of something called a law, which is kind of a general theory, a heavy-duty theory, you might say, that's been tested enough times so we have pretty good reason to believe that it's true. And we say, this is now a law. That doesn't mean that it always works. Somebody may disprove the law next week. But at least until they do, we can work on the assumption that it's been tested enough times that we can be reasonably sure that it works, that it's true. that it in fact reflects some observable reality in the universe, or if it isn't realistic, at least it might be instrumental. That is to say, it might be useful. We might be able to use it even though we're not entirely sure that it's true or realistic. Instrumentalism and realism are two different ways to look at scientific theories, and even if one considers them to be laws, to make use of them, whether they're objectively true or whether they're not. Philosophers of science actively study such questions as these. What is a law of nature? What makes it a law? How sure are we that it is a law? How did it become a law? What kind of data can be used to distinguish between real causes and accidental regularities? There are many things that we observe that appear to be causative, and they may not be. It may be that there's just a coincidence, that there's a correlation, perhaps, but not a causation. Sometimes things can show up over and over and over again, and we can think that they must be causative, and yet they can prove to be anomalies that are not really part of the cause. How much evidence and what kinds of evidence do we need before we accept hypotheses? How many times does the experiment have to be repeated? How many different experiments does it take? How many things do we need to nail down? How sure do we have to be? What kind of evidence would we accept before we can accept the hypothesis? And why do scientists continue to rely on models and theories which they know are at least partially inaccurate? For example, Newton's physics, which was regarded as state-of-the-art a couple of centuries ago, now people know it doesn't really work very well when you're dealing with things that move very, very fast, or that are very, very small, or that are huge, large, like planets, for example. So, why do people continue to use Newtonian physics? The answer, of course, is because it works, because it's useful. It is a valid instrument, even though it may not be real. But the question still comes up, why do scientists rely on these things when they know that they're not entirely true? When we try to determine what science really is, and ask the question what characterizes science as opposed to other kinds of study, we're really asking how scientific is something? Well, to know how scientific something is, we have to kind of look at different issues that make up the investigation of something from a scientific perspective. First of all, science focuses on the natural world. Secondly, it aims to explain the natural world, to tell why things in the natural world happen the way they do, and be able to predict what's going to happen with that thing in the future. Science uses testable ideas. If it isn't testable, it's just not science. Science relies on evidence, data. Science involves the scientific community. It's not done individually. It offers up its conclusions to the wider community for evaluation and testing. Science leads to ongoing research. Nothing settles everything. There's no one experiment that provides all the answers. Each scientific theory leads to the need for more scientific theories. Each experiment suggests new experiments. Every bit of truth that we discover about the universe opens up more parts of the universe that can be studied. And there are benefits from scientific behavior. Scientific behavior helps us to think more clearly and to understand better and to come to testable conclusions that other people can verify or disprove. And the benefits accrue to not only the individuals who are doing the work, but also society and even the world as a whole. Science is powerful, but it's not all powerful. It's generated a knowledge that allows us to call a friend halfway around the world with a cell phone, or vaccinate a baby against polio, or build a skyscraper, or drive a car. Science helps us answer important questions like which areas might be hit by a tsunami after an earthquake? How did the hole in the ozone layer form? How can we protect our crops from pests? Who are our evolutionary ancestors? With such breadth, the reach of science might seem to be endless, but it's not. Science has limits, very definite limits. Here are a few things that science does not do, and that a good scientist does not do. First of all, science doesn't make moral judgments. When is euthanasia the right thing to do? Science can't answer that question. Science might be able to say the most painless way to commit euthanasia might be, but it can't answer the question, when is euthanasia the right thing to do? What universal rights should humans have? Not a scientific question. Should other animals have rights? That's a moral judgment. Questions like these are important, but scientific research will not answer them. Science can help us learn about terminal illnesses and the history of human and animal rights, and that knowledge can inform our opinions and decisions, but ultimately, individual people must make moral judgments. Science helps us describe how the world is, but it cannot make any judgments about whether that state of affairs is right, wrong, good, or bad. That's another branch of philosophy called ethics. Another thing that science doesn't do is it doesn't make aesthetic judgments. Science can reveal the frequency of a G flat and how our eyes relay information about color to our brains. But science cannot tell us whether a Beethoven symphony, a kabuki performance, or a Jackson Pollock painting is beautiful or dreadful. Individuals make those decisions for themselves based on their own aesthetic criteria. Science doesn't tell you how to use scientific knowledge. Although scientists often care deeply about how their discoveries are used, science itself doesn't indicate what should be done with scientific knowledge. Science, for example, can tell you how to recombine DNA in new ways, but it doesn't specify whether you should use that knowledge to correct a genetic disease, or develop a bruise-resistant apple, or construct a new bacterium. For almost any important scientific advance, one can imagine both positive and negative ways that knowledge could be used. Again, science helps us describe how the world is, and then we have to decide how to use that knowledge. Here's one of my favorite cartoons. Science can tell you how to clone a T-Rex, but it can't tell you whether that's a good idea or a bad idea. Humanities can tell you why this might be a bad idea, because humanities is the study of history, it's the study of human nature, it's the study of ethics and ideas, and it can answer the question whether we should, not just whether we could. You may remember that in the movie Jurassic Park, the mathematician who's against the whole project from the start says to the scientists who created the dinosaurs from DNA found in mosquito blood, you guys were so busy asking if you could do it that you never stopped to ask if you should do it. And that's something that science isn't very good at. It's not really a scientific question, but it obviously can create some real problems. We can create an atomic bomb, but should we create an atomic bomb? We can splice genes, but should we splice genes? Those are not scientific questions, they're ethical questions. And another thing that science does not do, science does not draw conclusions about supernatural matters. Science, by definition, is the study of the natural world. Do gods exist? Do supernatural entities intervene in human affairs? These questions may be important, but science won't help you answer them. Questions that deal with supernatural explanations are, by definition, beyond the realm of nature. They are supernatural, not natural. And hence, they're also beyond the realm of what can be studied by science. For many, such questions are matters of personal faith and spirituality. Now, don't make the mistake of thinking that personal faith and spirituality don't rest on good, solid reasons. There are good reasons to believe that there's a God who made the world, There's good reason to believe that Jesus was a real live human being who lived and walked on earth and did things that people found amazing. There's a real reason to believe that he was crucified on a cross and buried in a tomb and that he was resurrected from the dead. There are good reasons to believe those things, but they can't be investigated scientifically. Of course, there are many things that can't be investigated scientifically, including most things that happened historically. Those things have to be investigated legally or judicially or historically. Science doesn't draw conclusions about supernatural matters because science is the study of the natural world. Okay, well, I hope this has been helpful to you. Remember that the exam is an online exam, and it will cover the textbooks and the important points that we talked about in class that I have tried to summarize here. So you'll be expected to know those things. And I hope that your future scientific world is a happy one and that you are better equipped to do good science now than you were able to do before. And may God bless you in what you do. From here on out, may you be a good student of the natural world.